Today our topic of discussion is MgO by alumina ratio in blast furnace slag. With the decline in availability of high grade iron ore, the topic is very important now, how to rely on high alumina rich ore. When we know as alumina rich ore contribute for high alumina viscous slag, and once slag viscosity increase, the operational efficiency of blast furnace decreases. In order to take care of such burning topic, the MgO by alumina ratio is being studied through a phase diagram, the viscosity measurement at lab scale, and few industrial data sharing is being done in subsequent slide to catch hold of MgO by alumina issue. As we know, the viscosity of high alumina slag in blast furnaces could be well taken care by addition of MgO. But addition of MgO is to be very precise decision making activity. If we increase the optimum amount of MgO, then only the decrease in viscosity of blast furnace slag can be done effectively. If we increase MgO content beyond a limit, then our melting point also shot up very high, where the inefficiencies of blast furnace start occurring. As this graph clearly shows, our center of operation is the yellow rectangle. As this shows very clearly how the melting point of slag shot up when alumina increases from 10% to 25%. As we can see from the graphical trend which is being narrated in this slide, is about the yellow region where MgO by alumina keeps within 0.4 to 0.6, and by doing this, melting temperature is well within the feasible range, that is around less than 1400. So we can say that based on those graphical trend, our feasible operation of blast furnace is in 0.4 to 0.55 region. Here with on the basis of a alumina scale, three segment control strategy is being discussed. The first segment of alumina is less or equal to 14%. The second band is in between 15 to 17% for MgO by alumina 0.4 to 0.5, and when alumina goes beyond 18 or equal to 18, MgO alumina remains 0.45 to 0.55 level. And the same thing is here reproduced in this slide, and it named three segment control strategy. Generally, in many cases, our furnaces undergo with a band of 20, more than 20 to 23% alumina. And for this slide is being made when our alumina level in blast furnace slag goes beyond this 20 level, 20%, then optimum MgO content will be less than 10%, and MgO by alumina ratio is to be kept around 0.55. Here I try to summarize that what is the impact of MgO. It is not that MgO can be used as an instrument to solve, to take care of any band. So optimization, in view of optimization of MgO, it is essential to know that what is the yield effect when it goes beyond certain limits. And this is some industrial case study based on this MgO by alumina ratio, where it shows that when fine tune of MgO by alumina, that is when MgO by alumina decline from 0.5 to only 0.43, how the techo-economics parameters improves in a bigger furnaces. Now coming to a bit short of a knowledge sharing on that how MgO works in diluting the viscosity of alumina slag. As it's shown, the mechanism Mg2 plus ion disrupt the network structure formed by Al₃ plus and Si4 ions. And for example, we can say that 18% alumina viscosity decrease from 0.5 Pascal second to 0.355 Pascal second when MgO alumina increase from 0.25 to 0.45. So this is a sort of a tremendous benefit for a blast furnace when this fluidity or the viscosity part of the slag is being taken care, and this improves our tapping efficiencies, the furnace drainages, wind acceptance, and so many things. Now coming to the MgO rise and melting point temperature increase mechanism. So this mechanism is basically happens due to formation of a marvinite, periclase, and spinel. These are very high melting phases, and MgO when added beyond a certain limit, these phases formation provoke, and that's why one example has been taken when alumina is 20% and MgO is more than 16%, and by doing that our MgO by alumina ratio goes beyond 0.8. At that time our melting temperatures goes beyond 1500 degrees centigrade, which is impractical for blast furnaces, and in such cases there is always a chance that incomplete melting of the hearth will be there will be slag buildup, and so many irregularities will occur in the blast furnaces. So MgO increase the total slag volume at a constant alumina, so higher slag generation will lead to higher fuel rate, and one example has been taken when MgO content increases by 2% and our slag volume goes beyond 10 to 15%, which leads to a high increase in fuel rate. Similarly, if we talk about a viscosity consideration, then we can see that for 15 to 17% alumina, optimum MgO alumina is 0.4, 0.5, achieve 0.3 to 0.4 Pascal second at 1500, which is operationally ideal. Similarly, our desulfurization ability is also to look into, because as we increase this MgO, we must have to keep basicity around constant, so CO will decrease. And we know that desulfurization capacity of MgO is almost zero point 0.7 times of CaO. So we can say that when MgO is added and CO is proportionally reduced, the overall sulfur removal efficiency may or may not improve unless basicity increase slightly. So we can say that this operational cost implication is also there when you have got a more MgO addition. Thus, MgO addition becomes a very important aspects to look into. So we can say that proper MgO addition is a very skillful decision, and of course this slide data and statistics and findings helps operators in deciding that at what band they should operate their slags. Thank you.